Okay, hi everyone. Today I'm going to present part of my PhD work on the optimal design of sandwich panels for multifunctional properties. I hope that you have understand that the main purpose of architectural materials is to fill some holes in the property chart, so I won't insist in this. What I want to emphasize here is that the materials properties of architectural materials depend on three main points. The first one is the material. For example, if you consider an architectural material made of aluminum, which is here, this is the first main point. The second point is the architecture. You can here consider two main architecture. It's the example which is illustrated here, which is an aluminum lattice and an aluminum foam. And the last point is the geometry, which describes the architecture. And playing with this geometry, you can reach for an aluminum lattice all this domain of properties in terms of Young's modulus and density with an aluminum lattice, and all this domain for an aluminum foam. Actually, for architecture sandwich panels, it's quite the same. You can play both on materials and on the geometry, meaning the thicknesses of each layer in a sandwich panel. Usually, sandwich panels are made of an architectural material as a core material. So here, it's important to consider both material selection and geometrical dimensioning in the design of such kind of structures. These structures have quite interesting properties. Here is a list which is really not exhaustive. This corresponds actually to the specifications that I investigated during my PhD work. But usually sandwich panels are considered as light solutions. They also have good structural properties such as structural stiffness and structural strength. And they also can be interesting for some functional properties such as blast resistance, acoustic damping, for example, thermal insulation, and thermal resistance. So here the big question is how can we consider a multifunctional set of requirements when designing an architectural sandwich panel. So the aim of my presentation today is to present a design method dedicated to architectural sandwich panels that simultaneously deals with material selection and geometrical dimensioning for multiple criteria. This will help to study the multifunctional properties of such panel, for example, in mass minimization, and this will also be used to study the influence of core architecture. I will base my presentation in a particular case study, which is the cabin noise reduction for helicopter makers, which is an interesting case study because here you want a panel which is stiff, which has a good structural stiffness, but also a sandwich panel which has a good acoustical transmission loss. The problem here is that usually stiff panels are not good for acoustic damping. There is a quite interesting article from Wang et al. On that subject. Actually, to increase the acoustical transmission loss of a panel, you can use two main effects. The first one is what I call the mass effect. Here you want to increase the mass inertia of the panel. When the panel is heavy, it's harder to transmit the acoustical wave through this panel. And the second effect is what I call a sandwich effect. In this case, what you want is to have a sufficiently soft core to allow here the occurrence of symmetric vibration modes, which added to the anti-symmetric vibration modes will limit the acoustical power which will be transmitted at the back of the panel. But here you can see that having a soft core can be conflicting with the fact that you also want to have a stiff panel. So my presentation today will follow this outline. I will first present the design process, and then I will treat the case of the optimal design of a foam core sandwich panel to treat the case studies that I've just introduced. and at the end I will talk a little bit about the influence of core architecture. So the design process here is a multi-objective optimization process. It's based on the Pareto set optimization, in which we are looking not for a single optimal solution, but we are looking for a group of solutions with different trade-offs. The central part of this design process is an optimization algorithm. In this case, is a genetic algorithm, which is already well known for structural optimization, for example, for composite structures. This algorithm will explore the design space, will generate some solutions, and these solutions will be evaluated using some analysis tools, and then it is possible to fill the performance space in which we represent each generated solution as a function of their performances. This is the case of, for example, a bi-objective optimization problem. Here we can use two different notions to rank this solution. The first one is the Pareto dominance. It is illustrated here. In this case, this solution is better than this one according to the two specifications here. So we say that this solution dominates this one. The second notion is the notion of Pareto equivalency, which is illustrated here. In this case, you have, for example, this solution, which is better according to this specification, but this one is better according to this one. So you have no dominance of one of these solutions compared to the other one. So here we say that we have a Pareto equivalency. And the optimal solution of our multi-objective problem can be defined as the group of solutions which is non-dominated in the performance space. This group is also called the Pareto front or the trade-off surface. It's shown here, for example, in this case. And each solution in this group are Pareto equivalent, meaning that all these solutions are optimal, but for each solution there is a different trade-off between the two specifications that we are optimizing. Now, as I said in the introduction, it is important for sandwich panels to consider both material selection and both the geometry. So here, to represent the sandwich panel, actually, you can consider two different approaches. The first one is based on a closed design space. This is specific for architectural materials, for instance. The first one is based on a closed design space in which you will consider a database in which you have some architectural materials, for example, foams, and all these foams are referenced according to their material properties, which are measured properties. So these materials, these foams, are real existing materials. In this case, your sandwich panel is composed of two materials and two thicknesses describing the sandwich panel. So this is what we call the real path approach, because you are dealing with real materials. This is what we'll do for material selection, both for the architectural material, which is the core material of the panel, and for the faces. Now you can also do what I call the virtual path approach. In this case, you consider your architectural material as described by first the constitutive material, for example, this one, and then the material properties of your virtual material will be calculated using scaling laws. And so the regions that you can reach using only one constitutive material can be represented here, for instance, for a virtual form. Now, if you consider all these materials as possible constitutive material, the regions that you can reach in terms of material properties, for instance, Young's modulus and density, is schematically this one. So here, when you consider this approach, what is possible to do is to consider different material, face constitutive material, core constitutive material, the two thicknesses, but also additional geometrical variables that will describe the architecture of your architectural material as core material. So what I'm going to present now is first bi-objective problems considering the optimal design of a foam core sandwich panel. First, for the flexural stiffness at minimal weight, which is half of the problem in cabin noise reduction. Then I will present the problem of acoustic damping. And at the end, I will present the multifunctional optimization problem. So in this case, when you treat the problem of flexural stiffness at minimal weight, my design space is composed of several face materials, some metals, polymers, and composites, with thickness varying from 0.5 to 10 millimeters. The core material is a foam. It can be either metal, ceramic, or polymer foam, with a thickness varying from 10 to 500 millimeters. My objectives are to minimize the central deflection if you consider a sandwich panel submitted to a 3-point bending test, and to minimize the mass per unit area. Now, if you consider material selection through a performance index method, you can identify a metal matrix composite, which is an aluminum reinforced with 60% of carbon fibers, as the optimal face material. You can do the same for the core material, and you can identify a PVC foam as optimal material. But with this method, you don't have the optimal thicknesses, and you don't have the optimal performances. So when you run your optimization algorithm, at the end you obtain the performance space, which is presented here. Here you have the mass of your sandwich panel, and here you have the central deflection. What you want here is to reach this point. Actually, here each point represents a different sandwich panel, and here what you have is the influence, the contour values of the 4 design variables that I've considered: the face material, the core material, the face thickness, and the core thickness. And in these charts, you can identify the optimal values of these design variables. For example, here, after data post-processing, you can identify this metamatrix composite as the optimal solution as face material. This is the solution that was identified through the performance index method. Now, when you look at the core material, you find that actually the space is divided in 2 parts. The first part corresponding to very stiff solutions made of glass foam, which is a very stiff ceramic foam, and the lightest solutions are made of a PVC foam. And actually here the transition is depend on the geometry of your solution. At some point it will be more interesting to have a thin glass foam core than a thick PVC foam core. This design guide here means that to increase the flexural stiffness of a sandwich panel, it is required to increase the core thickness. It's something that it's quite well known for a decade now. But here you can have some design guides which are interesting to design a sandwich panel for flexural stiffness at minimal weight. Now if we look at the acoustic damping at minimal weight, I have the same design space, but this time I want to maximize the mean value of the acoustical transmission loss in this frequency range, which is the frequency range of interest for helicopter makers. Now, if I use the method of performance indices, what I found is as optimal face material tungsten uranium alloy, which is a theoretical result, and as optimal core solution, a polyurethane foam. After optimization of this structure, effectively the polyurethane foam is the best solution. More surprising is the fact that here the optimal thickness of the core material is about 10 millimeters, which is the limit value of the core thickness here. So this is the first design gain. It corresponds to the core layer. In terms of face design, actually, what is important is to have a face which is which is designed by its mass, not by its material, nor by its thickness. So here the important is the mass of the face. So now if I look at the multifunctional problem, I just said that for flexural stiffness, it is preferable to have a thick and stiff core, for example, 10 centimeters of PVC foam. But for acoustic damping, it would be preferable to have a thin and a soft core, for example, 10 millimeters of polyurethane foam. If you treat this true objective case, you end up with a three-dimensional performance space. And if you look only at the solutions here with a mass per unit area of 50 kilograms per meter square, here is the kind of plot that you can have. The main interesting thing here is that the performance space can be divided in two regions. The first one that has a pointed shape here, which corresponds to solutions which are very stiff. In this case, the ceramic foam here is so stiff that you cannot have a sandwich effect for the acoustical transmission loss. So here, to increase both the mechanical stiffness and the acoustical transmission loss, you will increase the core thickness in order to increase both the mass and the distance between the faces. Here it is completely different. In this case, you have the optimal core material, which are PVC foam or a polystyrene foam, which are quite soft. And in this case, you have a sandwich effect. Actually, when you look at the influence of the core thickness on the mean value of the acoustical transmission loss, there is a parabolic relationship between these two variables. And when you add the peak value here, for polystyrene and PVC foam, the peak value corresponds to about 20 centimeters. So that's what you can observe here. When you want to increase the stiffness of these solutions, you will want to increase the core thickness, but if you do that, you will also decrease the mean value of the acoustical transmission loss, and that's what you see here. That's why you have here a convex trade-off surface in this case. So here you have a competition between two different design guides corresponding to the acoustic specifications and to the mechanical specifications. So it is important to have the whole trade-off surface in order to be able to determine what is the main mechanism you want to deal with in terms of acoustical transmission loss. Now, this is only valid for a foam core sandwich panel, and as I said in my introduction, it is important to be able to switch the architecture to see if it is possible to have better performances. So now I will use a virtual path approach to study the influence of core architecture, and I focused my work on two different groups of architecture. The first one, using the Maxwell stability criterion, the first group is the group of bending-dominated structures, for which you consider that the struts of your architecture, when it is mechanically loaded, these struts will deform by bending. You also have strain-shear-dominated structures. For example, the octatross lattice, which Remy showed you before. This structure, when loaded, the struts will deform by stretching. The interesting point with that is, for a given density, stretching-dominated structures will be stiffer and stronger than bending-dominated ones. In my PhD work, I investigated three different core architectures. The first one is foams, which is a bending-dominated structure. The second one is the regular hexagonal honeycomb, which is bending-dominated in the in-plane directions, but in the out-of-plane directions can be considered as a stretching-dominated architecture. And the last one is the tetrahedral truss core, which is stretching-dominated. Now, if you consider these three architectures as possible architectures for the core material of a sandwich panel, you can rank these architectures, and you find out that effectively, when you look at mechanical properties, for example, flexural stiffness, flexural strength, or blast resistance, stretching dominated structures are better than bending dominated ones. Here, in green, you have foam core sandwich panels. In red, here you have honeycomb core sandwich panels. In purple, it's the truss structure. If you look at some other specifications, such as acoustical transmission loss, for which you want softness in the core material, the more weight efficient structure is the bending dominated structure, which is foam in this case. Okay, so now if you look at the multifunctional design, in which you want both to have something which is quite soft for the core material, which is the acoustical transmission loss, but also something which is stiff, because you also have mechanical specification. The design guides can change. I won't discuss this too much. What you can see is just that here the design guides change because you don't play on the thickness of the core to tailor the trade-off between acoustical transmission loss and flexural stiffness, but you will play on the relative density of your core material. And what I want to show is here, when you look at the ranking between the architectures, you can see that if you look at very stiff solutions, the best solutions are honeycomb as a core architecture, but if you look at high acoustical transmission loss, it will be first truss structure, and eventually, if you relax this constraint, you will find out that foam is far better solution for acoustical transmission loss. So here you can see that it is difficult to select an architecture prior to the optimization process if you have some multifunctional specifications which can be conflicting in the optimal design guide. The last thing that I want to show you is actually, as I said, truss structures are stretching dominated, but when you see at these curves, for flexural stiffness, it is quite close to the behavior of a honeycomb. When you look at the acoustical transmission loss, the behavior of a truss structure is quite close to the behavior of a foam. Actually, this is due to the angle here between the face sheets and the struts, which has been constrained to be between 35 and 65 degrees in my optimization problems. And actually, in this case, the optimal angle is about 50 and 55 degrees. This is the optimal value to have both here compressive modulus and shear modulus. But in this case, what you want is to have something soft for acoustical transmission loss. So here, with one design variable, you have something which allows you to switch continuously from a stiff to a soft architecture. And that's make these kind of truss structures very interesting in terms of multifunctional design. So to conclude, as I said, the properties of architected materials and of sandwich panels depend greatly on both materials, architecture, and geometry, and this is really important to take this into account in the design process. By using a Pareto optimization, you have access to the whole trade-off surface, and this is important because with this you can obtain design guides which will change by changing the trade-off that you are looking for in your multifunctional problem. Actually, the real path approach is the more convenient for industrial problems because you work with existing materials. We had a collaboration with an industrial partner, and using this kind of approaches, we have been able to save about 100 kilograms on a mechanical structure, which was 600 kilograms for transport application. So it's something that really works. The last thing that I wanted to say is that the optimization by virtual path is really interesting because you can compare directly the architectures considering the same material and the same relative density, and you can see in the corresponding specifications which can be interesting for each architecture. Well, thank you a lot, and thank you for inviting me today.